So, hi everybody. I'd love to introduce Hamdi Tchelepi from Stanford University, where he's been doing a ton of work on subsurface geology modeling and particularly the GEOS project. Welcome.
Thank you very much, Greg, and thank you for the invitation to share our developments on subsurface CO2 sequestration. I am currently the chair of the Energy Science and Engineering Department at Stanford, and my team of students and postdocs, we work on several subsurface engineering problems, but our particular focus over the last decade has been on numerical simulation of subsurface CO2 sequestration at scale. So before I get into some of the details of the physics that we study, investigate, and model, I want to acknowledge my senior collaborators, those with whom we've had long and deep relationships. Randy Setgast from Lawrence Livermore National Lab, really the DNA of GEOS. If there is such a thing, you'll find Randy Setgast all over it. Josh White, the PI, the principal investigator from Lawrence Livermore on the Maelstrom project, which really underlies the code we call GEOS. Josh is also the co-PI of the continuation of this project, Maelstrom, which really started in April. Nicola Castelletto, also from Lawrence Livermore, he's currently the PI on this new Maelstrom project. And I have to acknowledge long-time collaborators and previous students of mine, Francois Hamon and Sergei Klevtsov. I also want to acknowledge the PIs from Total Energies and Chevron, who not only sponsor, but also work with us collaboratively on the development of the algorithm and the simulator. So just to keep things straight, Maelstrom is the research project that is significantly larger in scope than developing code. GEOS is the simulator, is the numerical simulation framework that takes the physics of the governing equations that describe the dynamics of flow and transport in the subsurface and implements them in a scalable framework that allows for very large-scale simulation of these technologies for storage. So why work on CO2 sequestration, and why now? I don't have to share much about this with this community. There is consensus throughout the community, even among the most restrictive pathways, aggressive pathways to reduce emissions. They all have a huge fraction of the storage of CO2 into the subsurface in order to meet the IPCC targets, whether you're talking regionally at the state level, at the national level, or at the global level. CO2 sequestration is expected to occupy a significant fraction of the total amount that we have to put away in order to meet the degree targets. So there are many reports that were sponsored by the Department of Energy in the States, but in many communities across the planet in Western Europe that basically describe the details of both the challenge and the scale that is necessary in order to put away CO2 safely at a scale that would make a difference. And this is the objective of today's meeting, is to talk about simulation capabilities that can be used to put away the CO2 at large enough scales to make a difference. And when I say large enough scales, you have to think of the many gigatons per year for the next 30, 40 years. That is a lot of CO2 to put away. It would be equivalent by many calculations to the entire size of the hydrocarbon producing industries today. We take out the equivalent of 100 million barrels of oil from the subsurface of our Earth, and we would need to reverse that process on that order, 100 million barrels a day for the next several decades in order to control the emissions challenge. So these are not just hypotheticals. There are several large-scale projects that are being planned and about to get executed. One important project is the Northern Lights project in the North Sea, and this is something that is a collaboration between Equinor, which is the Norwegian oil company, Shell, Total, and other parties are expected to ultimately join to realize the full cycle of taking CO2 and storing it safely in deep subsurface formations. So now we want to delve in a little bit into what we mean by sequestering the CO2 into the subsurface. So if you look at the cartoon here, you basically see that below the surface is a very complex system of formations that vary in composition, in properties, in fluid content, and so on and so forth. And with CO2 sequestration, the intent here, the plan, is to inject the CO2 deep enough into the subsurface so it does not interfere with water resources, potable water resources, and aquifers, but more importantly, deep enough so that the CO2 is in what we refer to as a supercritical state. Supercritical fluids tend to have densities that are more like a liquid. So the density of CO2 about 1,000 meters below the subsurface is on the order of 700 kilograms per meter cube. So it's more liquid-like, but the viscosity is a 20th of a centipoise. So think of water at the surface is 1 centipoise viscosity. CO2 in the subsurface is expected to be a 20th of that or thereabouts. So we do want to inject it in this supercritical state in order to maximize the mass we're putting away as we try to sequester the CO2 deep into the subsurface. So what does that entail? So first, you have to understand, yes?
What kind of CO2, I mean, are we talking about a gas coming into this whole process, or is it already some kind of a liquid formation that's been stabilized in some way?
So actually, the intent behind largely is to think of what we refer to as very large point sources. So think of a power plant that burns natural gas. You take the flue gases from the emissions, you capture them with some chemical or physical process to high grade the concentration of the CO2, and then you compress the CO2 to be in this supercritical state, and you inject it into the subsurface. So the idea here is to pair up large point sources, whether they are steel making factories, concrete making factories, power plants that burn hydrocarbons, but you take the flue gases and to prevent them from being emitted into the atmosphere, capture the CO2 with high enough concentration, compress it, and inject it into the subsurface, hopefully never to be seen again. But we'll talk about that.
Got it. Thank you.
Okay. So the challenges here involve a lot of aspects. Some have a lot to do with the geology, understanding the details and the properties of the target formation and its surroundings. If you have not heard anybody talk about flow in porous media, think of subsurface formations as your kitchen sponge that you use to clean dishes with. It's a solid material, but it forms a skeleton, and in the interior of that solid material are the pores that hold the fluids, those are the pore spaces where we hope to put the CO2 away safely and for a long period of time. So think of very large scale sponges deep into the subsurface, overlain by rock, and you're trying to figure out where to find them and to poke them in the right places and inject the CO2 and putting it away. So it's not just a question of understanding the geology and the material properties, but it's a huge question of understanding the dynamics of multi-phase flow of fluids and the interactions between the fluids and the structure that holds them, also the structure that surrounds them, because we want the CO2 to stay and not leak to the surface or contaminate other areas. So here is now a closer level of detail, a cartoon nevertheless. So in this cartoon, you can think of this target blue colored layer as the formation, the porous formation that lies more than 1,000 meters below the subsurface, in which you're injecting the CO2. And in brown, above it and below it, are the rock formations that surround this porous layer. Hopefully this top of the formation is leak proof, because it supposedly lies below a formation that is impermeable to fluids. Mainly think of it as a shale protective layer above that formation and below that formation. So in this cartoon, there is a lot of actually underlying physics, because if you put away the CO2 and you inject enough CO2 into the target layer, and then you turn the switches off, you're no longer injecting. This is what we refer to as the post-injection period. So you've put a blob of CO2 into the subsurface, and what happens is it's going to be mobile, because you are most likely putting it to displace resident saline water in this scenario. And the expectation is, as I discussed earlier, that the CO2 is less dense than the resident water, and it's also less viscous than the resident water. So it will creep up to the top of the formation and form what we refer to as a gravity current. So in this light blue color, now you have the CO2, and several things are going. There is an interface between the gravity current and the underlying water. That interface will have some of the CO2 dissolve into the underlying water. So an important point to mention here is that supercritical CO2 and saline water are expected to be immiscible with each other. So now you have two different fluids with two different viscosities and densities and wetting characteristics sharing the pore space, but some of the CO2 along the gravity current actually gets dissolved into the underlying water, and that density difference of the layer of CO2 saturated with CO2 with respect to the underlying of water without CO2, there is enough of a small density difference to drive a convective instability. So these fingers in the cartoon are gravity fingers that are carrying saturated CO2 to the subsurface. And we really like that, because you want to maximize the trapping of the CO2, making it immobile to enhance the safety of the storage. something happens in the back end of this gravity current as the CO2 moves, say, up dip in this formation. Water re-imbibes behind the CO2 into a system that then traps the CO2 in tiny, tiny bubbles in the pore spaces. We refer to this as residual trapping. So there are several things that we want to maximize. When we say trapping of CO2, these are mechanisms that enhance the safety of keeping the CO2 into the subsurface. The most obvious one is structural trapping, where you're assuming that, as I had in the cartoon in the previous layer, that the porous medium of interest is surrounded everywhere else by impermeable rock that prevents the CO2 from leaking. But in addition to structural trapping, especially with saline aquifers, you want to enhance the trapping through these processes of residual trapping, where the brine resaturates the CO2 and actually traps them at the microscopic scale in fully isolated bubbles. So this is the figure on the left here. So these blobs of black dots are the CO2 surrounded by water at the micron scale. And you would say, what difference does it make? It's the micron scale, but think of this micron scale being in a porosity that's 20% of the rock. So with huge rock subsurface formations, you can trap significant fractions of CO2 into the subsurface, never to be mobile again. The other trapping mechanism is what I showed you in the underlying current of the cartoon, is where the CO2 now dissolves into the underlying water with convective instability and carries the CO2 away from the top of the formation, making it mix with the water in a homogeneous way and staying into the subsurface, being no longer immiscible and no longer buoyant with respect to the brine. The ultimate storage that everybody looks for is for the CO2 to ultimately interact with the solid surface and turn into a solid. So the geochemistry of the formation will determine the time scale for this to happen. You want to remember, though, that you want to inject as much of the CO2 in its fluid phase to occupy as much of the porous medium as possible to go far and deep before the geochemistry takes its time to turn it into a solid. As of now, the entire focus of the CO2 sequestration community is on ensuring that we maximize structural trapping, we maximize residual trapping, we maximize dissolution trapping, and not rely in our plans on the geochemistry to turn the CO2 ultimately into a solid, because the timescales necessary for that tend to be way too long for us to consider and plan decisively. Again, there is an urgency here to act within the next few decades to put as much of the stuff away. And geochemistry, while desirable, is not the primary target of the scales of interest today. So a little more physics into the problem. So if you take the mechanisms at play here. So as I mentioned, we have multiple fluid phases with differing densities and viscosities competing for the pore space. The parameter space of the physics, in its simplest form, requires at least three dimensionless groups to describe the dynamics. One is M. Think of M as the viscosity ratio between the two fluids. The other one is the capillary number. Think of it as the ratio of the characteristic viscous pressure drop versus the capillary pressure, which the capillary pressure is the pressure that separates the interface between the two immiscible fluids. And then there is the buoyancy. Buoyancy is the ratio of the buoyancy forces to the capillary forces. And in the CO2 sequestration world, while a lot of people think that CO2 sequestration is simply the reverse engineering of the production of oil and gas, this diagram is a cautionary reminder that is not necessarily the case, meaning that in the parameter space where you're working with CO2 sequestration, you're almost smack in the middle of this parameter space where it's very difficult to defend a pure traditional Darcy scale representations. And it's very difficult to defend a pure invasion percolation dynamic. So here you're talking about competition between viscous and capillary forces in the presence of density and viscosity differences that make one wonder what is the governing equation needed to describe the physics of the problem. So this is just a cautionary reminder that many of us are still working on figuring that out. In the meantime, we have to make progress. So we are making our simulation codes based on a Darcy representation that is tuned to the physics of CO2 water systems for the specific target of interest. So the interesting science and engineering questions related to this space, again, what physical mechanisms are involved, what length and time scale do we need to describe the physics in order to be predictive, what is the governing set of equations that couple these systems, can we use experiments both at field scale and in the lab to better understand the dynamics, and then how can we put all of that information together into simulation models, based models that allow us to plan and execute these systems. Now I want to get a little more into the modeling dynamics of these systems. So this is a movie of a simulation that describes the convective dissolution of the CO2. This is simply to indicate that the dynamics of these systems are very, very sensitive to the interfaces separating the CO2 from the underlying water. And this is a reminder that if you only assume that diffusion will take place to mix the CO2 with the water, you would be underestimating the amount of trapping that takes place because of these convective mixing currents or fingers that carry significant amounts of the CO2 read in this simulation. It can take significant amounts of the CO2 as it dissolves in the water, carrying it deep into the formation. So in order to understand this gravity-driven instability, you have to resolve the length and time scales that would allow you to resolve the initial perturbations, but also the length and time scales and the right numerics to be able to model these convective fingers accurately. So that places a huge burden on the numerics that you can put together.
So question here.
Yes.
So in some ways, this is just showing a standard fluid dynamic simulation, which can get terrible, right?
Yeah.
So how is it just like a bunch of dropping fingers complexity, yes, or is it more like turbulent, like a really instability kind of flow?
So it's actually a convective miscible fingers. It is not so the Reynolds number here are very, very small.
Okay.
But the near chaotic nature of the early evolution of the fingers is as difficult to model as in turbulence, where you would miss the dynamics if you only do Reynolds averages without accounting for the instability. So it's a challenging problem. The other thing that you want to think about is that the length scales associated with these perturbations to start the fingers could be very, very small, on the order of centimeters. And the size of the formation of interest could extend tens of kilometers. So at what level of detail do you want to model these dynamics, and how do you carry that information as you try to model a system that's as large as tens of kilometers in areal extent into the subsurface and possibly hundreds of meters thick. So the computational fluid dynamics become quite complex and quite computationally intensive in order to model these systems at scale. And that is the kind of thing that I will try to touch on as I proceed.
And one thing would be,
Yes.
I'm not sure if it's a now slide or a little bit later, is how much data do you have available about the shape of these formations, or you have synthetic formations right now?
Yeah, no, actually, so that's a very, very good question. So the uncertainty associated with the predictions is very closely tied to how much information you have about the resolution of the characterization of the specific target formation you're after. It's actually a very big piece of the puzzle, is to say you're providing a range of predictions subject to the amount of information, and you want to continually update that information as you measure and monitor and experience the actual process of putting the CO2 away. So it's a forward problem that should be enriched by inversion as data gets collected.
Got it. Okay. Oh, of course, then the next question is, what data do you expect to have?
I will get into it. So yeah, no worries. So another set of simulations now to account for the two-phase flow nature of the problem. So in the top panel, you basically have what we refer to as saturation. So this is differentiating between the immiscible CO2 from the resident brine. And you can see how this gravity current is moving. The light blue is because the CO2 is getting trapped as the water imbibes in the back end of the gravity current. And the plot on the bottom is basically giving you the total mass of CO2 that is now dissolved into the underlying brine. And you can see that you can get a favorable set of conditions where the gravity current of what you injected gets completely arrested. It's no longer moving because the CO2 that used to occupy the gravity current has done two things: has either dissolved into the underlying brine or has been trapped as a residual phase in the back end of the current. And this is exactly the kind of scenario that you would want, say, in a large-scale aquifer, where you cannot guarantee that the aquifer is structurally containing the entire system. So you can think of an open system where this layer extends way beyond the gravity current that is safe and sound because the CO2 never gets the chance to occupy anything other than this layer. It is trapped, and it is safely trapped in such a geologic formation. So this is one area of investigation to expand the storage capacity of CO2 globally. That is to look for very large subsurface aquifer systems that are not necessarily completely closed, but where you can secure large amounts of CO2 injected safely if you know how to figure out how to balance the amount you inject with all of the trapping mechanisms to prevent the CO2 from staying mobile after a certain period of time. So again, so the solution rate, the amount of CO2, is a very strong function of getting the dynamics right. And getting the dynamics right also means that the computational resolution of your reservoir simulation needs to be able to resolve the length and time scales associated with the dissolution. And there is really significant sensitivity to the resolution before you get grid converged results of your numerics. Just like with any CFD problem, you have to worry about the convergence rate of your numerical schemes in order to say something definitive about the physics. You asked about this uncertainty and the available data You can see from this plot, first, there is this very difficult challenge of the combination of a very highly heterogeneous subsystem, subsurface formation, where the permeability, which is the ability to conduct fluids in the subsurface, the permeability can vary by orders of magnitude. The sizes can be huge, on the order of kilometers, to be of interest to store CO2 at large scale. But the physics really is governed at the pore scale. So the interfaces between the fluids have to be understood. So you have this combination of a highly heterogeneous, large-scale subsurface formation, and you only have very limited information, perhaps a few cores from the few wells that you have drilled into the subsurface, perhaps a few logs from the electronic logs that can measure the properties of the formation. More often than not, you have some seismic information that help you map, but the resolution of those things is not that great. And then you have all of the knowledge about the structural and regional geology in order to map out the properties of the system. So this combination of severe heterogeneity and limited information means that any prediction you make relies on populating the reservoir properties elsewhere in places where you don't have measurements, consistently with the available information and the geologic correlation structures that you have. So any prediction you make is a strong function of the quality of the reservoir model you construct. In order to do this reasonably well, you have to place this into a Bayesian framework where you say any model you construct is only one of many possible outcomes. And the solutions then will have to be provided in terms of probability density functions and confidence intervals and so on and so forth. I'm not going to touch on this uncertainty quantification component beyond this point, but you want to keep in mind that this adds to the computational burden on the ability to make predictions. So you need a high resolution model to resolve the dynamics of these multi-scale systems, but then you need many, many, many of them in order to make predictions in the form of distributions about where the CO2 is stored, where is it going, what is its fate. You can talk about confidence intervals depending on the specific site of interest. So again, we focus in this work of GEOS on the dynamics of the flow and the transport, but the inputs rely on a lot of other information from geology, stratigraphic modeling, seismic modeling, geostatistics. And like everyone else, we think we're the center of the world, so we place reservoir simulation at the center of this complex system. But it is made up of many, many subsystems to enable you to construct the models and perform the simulations. So now I want to talk about some large differences between worrying about CO2 sequestration and in terms of putting it away, and reservoir engineering practice in terms of the current practice of extracting hydrocarbons from the subsurface. When you're worried about putting the CO2 away, not only do you have to worry about the target container. In this case, this is this little parallel pipette sitting in the larger domain. So that's the target that you want to inject things in. And as you zoom in, it can be a very complicated heterogeneous system with wells and injection scenarios and so on. But you really need to think of it as a container surrounded by all of the overburden formations that are a kilometer above you or maybe more. And you want to worry about the interactions between the fact that you're changing the containers, pressures, and material strength as you inject the CO2. And those interactions between the target formation here, the little red thing, and the surroundings, those need to be modeled and accounted for. Because when you inject CO2, the two things you don't want to see happen. One, you don't want to induce earthquakes that can interfere with other subsurface formations, but more importantly, with the ecosystem on the subsurface where we all live. So you don't want to see induced earthquakes due to injection. That's why geomechanics is important. And you also want to make sure that it doesn't leak. The CO2 does not leak through subsurface pathways beyond the container that is the target of the injection. So with CO2 sequestration mechanics, not only fluid dynamics, but structural mechanics, poromechanics, the interactions between the pore space occupied by the fluids and the solid matrix that holds them. Those interactions are order one and need to be accounted for. So now you have to worry about resolving all of the details of the interactions between the structure of the container and all of the surrounding structures, possibly all the way to the surface, in order to model the dynamics. So you put the pieces together. Now you have multiple fluids sharing the pore space, CO2 as a supercritical state. I focused entirely here on saline aquifers, but a huge interesting target are depleted oil and gas reservoirs, so that you can literally reverse the process, but now put the CO2 away in places where you had produced oil and gas. So in those cases, the fluid dynamics get more complicated because it's not just CO2 and water, it's CO2, water, and hydrocarbons with multiple fluid phases. Now you have to worry about the interactions with the fluid structure dynamics. So you have to account for fluid flow, you have to account for structural interactions. Into a subsurface, you have limited information about. Into a system that is very likely highly fractured, and you may even want to induce the fractures in order to create a permeability to put away the CO2. So now you're talking about fracture dynamics, fluid mechanics into a heterogeneous subsurface formation at scale. So the mechanisms become very daunting to model at these scales. You have to worry about the fractures, their initiation, their interaction. Now you have to formulate problems that are multi-scale in order, think multi-grid, but for nonlinear dynamics, in order to solve the problems in reasonable time with reasonable computational resources. And we work on all of these aspects. We work on understanding the physics at the fundamental scale. We work on developing multi-scale formulations of these systems. We worry about coupling flow and geomechanics. We worry about the discretization and developing nonlinear solvers that are sensitive to combining the dynamics of multi-phase flow and mechanics. And we do all of this with the target of putting the stuff away in a simulator into a numerical code that is scalable. And this is where the GEOS computational framework comes in. The GEOS computational framework basically takes the discrete form of the governing equations that we have and the discretizations that we adopt on the nonlinear solvers and implements them on scalable large-scale architectures so we can solve these problems with high fidelity, but in a scalable manner to allow for accurate modeling of these systems. So here I'm going to keep it at a very high level and just describe what the requirements are and stop in a few minutes for discussions about these challenges. So the simulator that has been under development now for more than 5 years and builds on the architectural components that the Lawrence Livermore computational mechanics and high-performance computing people have been working on. The simulator takes in unstructured geologic formations with faults and fractures, allows for the solution of the tightly coupled flow, transport, and geomechanics problems, reflects an implementation of multi-scale algebraic and geometric solvers and formulations, and achieves near peak performance on the current and the next generation architectures. And we are putting out results on these findings with the use cases on a regular basis. So you can ping me or just Google GEOS and you'll find a great deal of information about the use cases, the ability to use the software, which is open source, and so on. The design of GEOS, and we put this to the test every day, is for the team of developers, which include scientists, postdoctoral fellows, and graduate students, for each of them to see a highly modularized framework so that they can focus on modeling the particular aspects of the physics that they're interested in. The users see a unified interface to the code, and it's an open source license to allow for everybody to have access to it, regardless of whether you're a large organization or a small nonprofit organization interested in modeling CO2 at scale. So a description of the Milestone project and the GEOS code at a high level. It's really combining forces of multiple organizations. So at Stanford, we've had a very long history of building reservoir simulators for flow and transport in porous media. In Livermore, there is a long history, a distinguished history of doing geomechanics and high-performance computing, all the way to actually co-designing the hardware architectures. So we've taken full advantage of that. And the sponsor, Total Energies, brings in both the incredibly important use cases of CO2 systems they want to use to put away large amounts of CO2, but they also have the internal expertise with high-performance computing, and we have a collaborator team that includes Total Energy scientists in the group. And now we've added Chevron as a full partner. Couple of words, and then I'll stop. So one has to break down the complexity of the problem. So we want to make sure that we decompose, if you will, the physics from the algorithms, from the computational numerics for high-performance computing. So we've paid specific attention to the physics solvers, the underlying fundamental formulations of the constitutive relations, and we've designed multi-level solution algorithms, both at the linear level with things like algebraic multigrid and geometric multigrid, but also at the nonlinear level with multi-scale finite volume and multi-scale finite element formulations and solvers. So the challenges are many and they continue, but the code GEOS today, I would claim, is the most advanced code that one can use to model flow and geomechanics and large-scale subsurface formations. So you can use it as of today with the capabilities that are in hand, but we continue to evolve the computational framework as we move forward. I want to mention here that GEOS is the piece of the puzzle that deals with the modeling of the fluid dynamics of the CO2 sequestration. It builds on an enormous infrastructure of things like Raja and Chai and underlying architectures to manage memory, manage computation, be architecture sensitive, but at the same time not require every user to change their code when you go from CPUs to GPUs to hybrids to whatever comes next. So there are layers of abstraction that sit between the physics model and the implementation on hardware architectures in order to maintain scalability, but to also maintain modularity and allow us to continue to evolve the GEOS framework, both as a research platform, but as a delivery vehicle for people to use. I'll stop here. I know I kept it at a high level, but I'm happy to entertain any questions about what we do with GEOS and how we think about CO2 sequestration. Any questions?
Thank you very much, first of all. Any questions on the call? Well, then let me begin with, how do you validate this horrible thing? You have little data and a lot of complexity.
Yes. So there, you really, one can learn a great deal from the reservoir engineering community that manages oil and gas, and also the water resources community that manages subsurface formations. So you have to constantly define the forward model in the context of equally probable models that can be constructed subject to the available data. And the available data really comes into multiple levels. One is understanding of the structural geology, understanding of the regional geology, but then for a specific target formation, you need things like seismic information, and then you need to constantly adapt your model as you experience the process of putting a well into the subsurface, logging it, and conditioning the model on the available data and on the dynamic data as you collect it. So you have to couple the forward and inverse problems on an ongoing, continuous basis, not just for monitoring, but also for planning and changing plans in terms of the injection scenario, the amount of things that you inject. The other thing that we hope will happen is that if you want to operate at the basin scale, you start from places you know very well. And then as you collect more and more data dynamically from the injections, from the seismic monitoring, from the deformation, even from satellite data of surface changes, you will increase your confidence in the next project that you undertake and in the next project after that. So there is no denying there is a great deal of uncertainty, but it is manageable because you can integrate the forward and inverse models, and you can take all of the experiences from the oil and gas global industry that is producing 100 million barrels of oil and use that collective expertise and knowledge to now put the CO2 away in large amounts. But again, there will always be uncertainty with these projects.
Yeah, that makes a lot of sense. I guess how, to what I guess as you're doing the backward solves,
yes,
what elements are you unsure about? Is it the subsurface geology, or are there parts of your physics approximations that you're not sure of their validity region?
So actually, the nice thing that we think the confidence levels in our ability to model the physics at the pore scale, we think that is in excellent shape, because we can perform, and we have performed experiments at cores of systems that are exactly the kind of systems you want to inject in. So if one could define the full details of the geologic structure, then we are in excellent shape. So much of the uncertainty really is in the details of the geology of the specific target formation, and also the details of the mechanical strength and moduli of all of the underlying layers between the target formation and the subsurface. So if you could, by a magical wand, get high resolution geology everywhere, then the confidence level and the design parameters would lie within a very small region in terms of the fluid dynamics. Yes, it's complex, but we think we understand it quite well, and we can approximate it with high levels of accuracy.
Great. And then how are, I think,
yeah,
how is this particular simulation with your particular goals related to the simulations that are backward solves to figure out this subsurface geology, or like at Stanford you have Mineral X, which is it's more for minerals, but still the same overall system, but you don't have all these fingers and this particular fluids interacting.
Yes.
But a lot of these seem to be kind of similar. You have these meshes that are discontinuous because you have tracks under surface.
Yes. So the inversion, we take advantage of any available information that you can collect, including active and passive seismic. So active seismic is meaning you go with a seismic survey to really target the formation, is very, very popular in the oil and gas industry. Mm-hmm. So you can use active seismic surveys to get better and better understanding of the system, but that still will only resolve things at the many meter scale. So even when you simulate, you want to simulate allowing for discontinuities that are consistent with the probabilistic model. So you can't take the discontinuities away. You have to simulate them, and you want to simulate the fluid transport in the presence of these discontinuities as a simulation framework. If you smooth out all of these discontinuities in order to say, well, we don't have enough information, so we might as well use a smooth model everywhere, then the simulations will really be worthless, because the interactions between the heterogeneity and the discontinuities have an order one impact on the evolution of the nonlinear dynamics. So you can't smooth the input model. You have to draw it from a probabilistic distribution. You end up with all of these discontinuities in every model, but then when you average, you're averaging the results of nonlinear high-resolution simulations consistent with your understanding of the heterogeneity. This is what makes it a daunting task. You have to account for heterogeneity, which is highly discontinuous permeability fields. You have to account for the presence of fractures, even though you don't know exactly where they are, but you can't smooth them out because they're important to the physics. And then you have to do all of these computational models with high enough resolution to resolve the fluid dynamics, the nonlinear dynamics, like the fingering I showed you. And then you have to cast a prediction within a probabilistic framework so that people can design these models and can use your simulation framework to design it, but also to monitor and mitigate as things go wrong. So we're advocating that you do a simulation-based forward and inverse model that is site-specific, that is used to design, monitor, and come up with mitigation strategies for the system. So basically, the word digital twin is used and abused, but we're arguing here for a digital twin of the target CO2 formation that lives with the evolution of the injection project, and as importantly, the post-injection period where the CO2 is mobile and you still want to know where it's going, and you want to monitor it, and you want to simulate it ahead of time, and you want to make predictions that add to the confidence.
Makes sense. Now, I'm trying to figure out what role machine learning plays. In some ways, it's obvious that UQ and like all the backward stuff is the standard Bayesian stuff. Mm-hmm. But one thing you just mentioned is there's a generative process where you say, here is a smooth model based on seismic data. I have to generate a rough model that's consistent with the smooth data and probably a distribution of such models.
That's exactly right. Actually, this is an area I don't work on, but we have colleagues at Stanford, Biondi and his group, and geostatisticians that work on that. That's exactly right. So you can take noisy data that has both signal and noise and seismic, and generate rough models that are consistent with correlation structures of the geology and the heterogeneity informed by other sources. And then you want to do the forward model with the fluid dynamics, generate additional rough models for the forward problem to enhance the confidence. So machine learning can be used to both enhance the training set by generating rough models consistent with the data, but machine learning can also be used to digest the data to understand the nonlinear evolution process of the forward and inverse problem, right? So, so nonlinearity sits at the heart of this problem. High resolution, high dimensionality sits at the heart of the problem. So there is enormous room for machine learning and network-based computing to generate models, understand data, assimilate simulation data, because the simulator can be used to actually generate nonlinear solutions that your machine learning model can learn from, so that the next time you do stuff, you don't start from scratch. You start from a machine learning model that has learned from the basin in which you've developed all of these simulators and you've collected all of this data. This can be digested on an ongoing basis by a machine learning model.
Yeah, that makes a lot of sense. And let's see, based on time, just one more question. So there's an HPC component here where, let's say, most Livermore computers are going to be the very large scale thing all in one spot. But most users have departmental scale or even cloud. You're going to have a rack or a few racks, but no more with a, the high quality network doesn't extend in clouds beyond a rack or two. Yes. So what scales is this code applicable for?
Yeah, actually, excellent question. In this case, and my collaborators will probably cringe. So GEOS, in a sense, can be used as the Ferrari framework for very high resolution at a scalable computer that's only available to a few. But you can also use it at much lower levels of resolution in order to get a sense of the dynamics. And preferably, long-term, what we would like to see are these multi-fidelity models, where some models are run with high resolution at very large cost in a scalable machine, but the rest of the ensemble can be sampled by lower resolution models with possible interpolation that comes from things like machine learning, generative network models to interpolate the nonlinear space, combining a few high fidelity models, a large number of low resolution models, but where the calibration between the high fidelity and low resolution is done through both machine learning and these multi-scale formulations that try to consistently translate information from the finest scales to the largest scale. So we think a combination of these capabilities will make it possible to do CO2 sequestration by the most prosperous nations on the planet like ours, or people who really need to put the stuff away, who can only afford a few low-resolution simulations, but perhaps with support from people like us and others, can calibrate their models with a few very high-resolution models with help from the national labs and from our resources. So hybrid efforts for both forward and inverse problems with machine learning support and multi-level exchange of information on an ongoing basis, we think can serve as an excellent basis to really scale the deployment of CO2 everywhere. I mean, for this to make a difference, we have to put away the stuff at the gigaton scale. It cannot be. It cannot be the toy project for Stanford and others. It has to be deployed at enormous scales everywhere on the planet for it to make a difference. And we think that a tool that can be operated at multiple levels of resolution, all the way from your laptop to the largest machine on the planet will help achieve that vision.
No, it makes a lot of sense. And just to tweak the scalability question a little bit,
Yes.
It's clear what you said about having multiple resolutions as different simulations.
Yes.
Do you have support for, I don't want to say multi-grid, but it's multi-resolution within the same run where the high interest area around the well site? I mean, honestly, we care more about the next 100 years than we care about the next 1,000 years.
Yes.
Because we'll hopefully be better by then.
Yes.
So on the well site matters a whole lot more than far away from the well site. But that means two very different meshes in these regions and costs.
Yes, yes. So actually, we don't do adaptive mesh refinement per se. So I saw the brilliant talk by Phil Colea in your but others have used it, and there is nothing that would prevent us from doing adaptive mesh refinement. However, Greg, what is really important here is that for a given resolution of the reservoir model, you can make it as small and as highly resolved as possible. All of our algorithms take that resolution and applies the equivalent of multi-grid, but at the nonlinear level, by constructing a hierarchy of scales from the given scale in order to solve the problem itself. So think of multi-grid applied as a solution strategy to any given resolution. The simulator behind the scenes takes your finest resolution, but internally builds a hierarchy, algebraically, a hierarchy of models in order to transmit global information efficiently, just like in any multi-grid method. So the underlying algorithms intrinsically apply a multi-level strategy for any given resolution. But you could definitely add on top of that dynamic adaptive mesh refinement to, say, resolve the transport dynamics more accurately near wells than elsewhere. And actually, we are embarking on things like adaptive implicit methods and mixing implicit and explicit treatment of the transport, and maybe ultimately go for dynamic mesh refinement.
Interesting. Actually, let me throw one more thing.
Sure.
Parallel in time?
Yeah, I would love to see that. Actually, Francois Hamon did a postdoc in Berkeley looking at this. I think these are very, very promising. But none of that is in GEOS today.
Oh, yeah, this is hard stuff.
Yeah, but it's hard stuff. But I think the promise of parallel in time and asynchronous discretization that allows you to evolve different PDEs in different parts of the parameter space at different time levels is something we're very, very interested in. But I must admit, is far from seeing it in something like GEOS over the next couple of years.
Right, of course. No, but this is fascinating. Thank you very much.
My pleasure.